Record instructions.
Bismillah Rahman Rahim. Okay, today we will discuss the analysis and design of two-way slab system without beams. And as you know that they are called flat plates. When there are no drop panels or column capitals and flat slabs, when drop panel or column capital exist. So in other words, we will discuss the analysis and design of flat plates and flat slabs. There are two sessions in this lecture. In session 1, we will discuss the flexural analysis and design of two-way slab system without beams using an analysis method which is called as direct design method. And in session 2, we will discuss the shear design for two-way slab system without beams. Because there are no beams, so punching shear is usually a problem in flat plates and flat slabs. So we will also discuss how to eliminate and overcome this problem of punching shear. So first of all, let's discuss the session 1 flexural analysis and design of two-way slab system without beams. The topics to be addressed today in session 1 are the background of this topic and introduction to direct design method. What is direct design method? What are the limitations? And how is this method used? And then the frame analysis steps using direct design method will be discussed in detail. Then we will solve one design example. And at the end, we will also discuss two-way slabs, other requirements of the ACI code, and then example 2 and 3. Finally, a summary of the direct design method will be discussed. So this is all with regard to the session 1, flexural analysis and design of two-way slab system without beams. Objectives of the lecture are that at the end of this lecture, the student will be able to analyze flat slabs and flat plates for flexure using direct design method. And the students will also be able to analyze and design flat slabs and flat plates for shear. Okay, first of all, let's see the background of this analysis and design of flat plates and flat slabs. We have seen in the previous lecture that a 90 by 60 feet hull was analyzed as a one-way slab system using several options. And these two options were primarily discussed in the lectures before the midterm. In option 1, there were beams 60 feet long beams running along 60 feet side of the hull, and all the slabs were one-way slabs because the ratio was more than 2, and we analyzed the one-way slab using the step method of analysis, and then we also analyzed and designed beams because the beams were simply supported on the wall. So we analyzed the beam using the exact method of analysis or the exact equation of WL square by 8, and then we design all the beams. This was the option 1. In option 2, 2 columns were introduced and a girder was also introduced along 90 feet side of the hull. And with this, all the beams which were in option 1, 60 feet long, are now divided into 2 spans 30 feet each. This was done in order to reduce the depth of the beam, which were 60 feet long, and in that case, the depth of the beam was 60 inch. So in order to reduce the depth of the beam, girders, one girder in 2 columns were introduced, and in this case, then the 30 feet long beam was only 24 inch deep. Okay. However, in this case also, the slab were analyzed as one-way slab because the ratio of long to short side was more than 2, and slabs where the ratio of long to short side is more than 2 is called as one-way slabs. So slabs were analyzed as one-way slabs. Then the beams were analyzed as two-span beams using the ACI moment coefficients of WL square by 9 and WL square by 11 for positive and negative. Girder was analyzed using the exact method of analysis, moment distribution method. Then columns were analyzed in design, and this option 2 was completed. Okay. Then before the midterm, we also discussed another option with the almost the same dimension, this time 100 by 60. And instead of 2 columns, 6 columns were introduced inside this hall now, and the purpose was also set to have been changed from a hall to a commercial building. So now the situation is such that there are panels where there are slab panels where the ratio of long to short side is now less than 2, and every panel is basically now representing a two-way behavior, two-way slab system. Okay, so we said that then this will be analyzed as two-way slab. The beams were running on the column center line in both the directions, along the long and short directions. Every panel was 25 by 20 feet. Long to short side ratio was less than 2, and every panel was analyzed with the two-way slab ACI moment coefficient method. In the ACI moment coefficient method, if you remember, there were tables, and we use those tables. The tables basically depend on the end condition of the slab panel and the short to long span ratio, which is just called as M. So after the M value and the end conditions were chosen, then the relevant tables were used to pick up the value for moment coefficient, and all the moments were then calculated, and this slab system was analyzed and designed. Okay, so this was moment coefficient method. In today's lecture, this system, which is 100 by 60 feet, basically 100 by 60 feet system, will be analyzed and designed with almost the same configuration as given in this slide, but without beams. When there are no beams, then the moment coefficient method cannot be used for analysis. Okay, so we will be using another method which is called as direct design method for the analysis of this system without beams. Okay, now in the same 100 by 60 feet commercial building is shown on the previous slide. If there are shallow or no beams, moment coefficient method cannot be used. Shallow beams mean when the beams are not very stiff, which means that depth is very small, then they will not provide enough resistance to the slab to minimize the deflection of the slab at the location where beams are provided. So because in the moment coefficient method, the basic assumption is that beams, if provided, must be stiff, and when beams are stiff, then moment coefficient method is applicable. And this condition is due to the reason that if beams are stiff, then the slab movement, the slab deflection is restricted or minimized at that location. If beams are not stiff, which means that if they are not deep enough, then the deflection will not be minimized at that location. The slab will deflect at that location, and the basic assumption of the moment coefficient method will be violated, and therefore moment coefficient method will not be applicable. Okay, so if there are no beams or shallow beams, then if moment coefficient method cannot be used, what else we can do? We can use this direct design method, which is basically a method of analysis, not a method of design. Although the name is direct design method, it is basically a method of analysis. You have seen in the previous several lectures that overall design process basically consists of 4 steps. In step number 1, we select sizes based on either the ACI minimum deflection or minimum depth criteria, or from the designer's experience. We select sizes of different members, slab, beams, and columns. In step number 2, we calculate the loads. Okay, the dead loads are calculated very easily from the section dimensions, from the member dimensions, and the density of material. And the live loads are taken from the AC tables. Okay. Then in the third step, the system is analyzed. And in the fourth step is the design step. And in the design step, basically, we calculate the reinforcement and AS, and the reinforcement and is then converted into the diameter of bar and the number of bars or the spacing of bars. So although the fourth step is basically called as design step, this overall design process contains one of the most important steps of analysis. And you have seen in the previous several lectures that analysis is one of the major steps and difficult steps, one of the difficult steps. And you have also seen that we had to struggle with the analysis instead of the final step, which includes the calculation of reinforcements. So most of our time was utilized in analyzing the system. If you remember, in all the previous lectures, the moment coefficient method for two-way slab was also a method of analysis. The approximate method of analysis which we used for the beams and the one-way slabs was also a method of analysis. You should remember that in the ACI code, these approximate methods are permitted to be used as an alternate method. This is not the main method of analysis. The ACI code strongly recommends that the designers use the more rigorous method of analysis, such as finite element method of analysis using a software such as SAP 2000 ETAPS or other software, commercially available software. However, the ACI code also permits to use alternate method of analysis for verification, or if the software is not accessible to a designer, then these methods can be used as main method of analysis. Okay, so all these methods that we have been using in this course for analysis are basically approximate methods of analysis, and these methods are recognized in one or other form by the ACI code. If you remember, in the we have clearly said in the previous lectures before the midterm that this ACI moment coefficient method for two-way slabs where there are stiff beams no more exist in the ACI code for several reasons that have been explained in that lecture. But still, the ACI code allows us to use the moment coefficient method, although it is not part of, it is not formally part of the code. Similarly, the direct design method has been recently taken out of the code. And as I said earlier, the direct design method is a method of analysis. Okay, I'm saying this again and again. The direct design method is a method of analysis, and this analysis method is used for slabs where there are no or shallow beams. If the beams are stiff, then ACI1 coefficient method is good enough. That has been used, and we have been using this method since long. Okay, and this gives us, this is giving us satisfactory results if we compare the bending moments obtained from moment coefficient method with the rigorous method of analysis like finite element analysis using SAP 2000 other software. Similarly, direct design method, which is a method of analysis for two-way slabs without beams, has also been compared, and it also gives us good results if you compare the results of direct design method with the SAP 2000 or SAP results. Okay, so although the direct design method has been recently taken out of the code, still it can be used. Still it can be used with its limitations, which will be discussed in the next slides. Okay, direct design method, as I said earlier, is one of the methods for flexure analysis of two-way slabs with or without beams. DDM is relatively difficult for slabs with beams or walls. Therefore, we'll use it only for slabs without beams. So Although in this lecture, we will be using direct design method for slabs without beams. The ACI code permits us to use this direct design method for slabs with beams. But what we have seen is that the DDM, direct design method, is relatively difficult for slabs with beams. If we want to analyze slabs with beams using direct design method instead of ACI moment coefficient method, then DDM is difficult, relatively difficult than the ACI moment coefficient method. However, if DDM is used for flat slabs or flat plates where there are no beams, then it is a very straightforward and very easy method, as you will see in the next slide. Very straightforward, very easy. Okay, and in just one or two steps, you are able to analyze the system. The provision of ACI 3.18.14 for DDM have been removed from the latest version ACI 3.18.19. However, it may still be used for the analysis of two-way slabs system. This, as I said earlier. Okay, now this was the background of all this. Few more things before we start the direct design method, which I said quite a few times now that it is a method of analysis. Although the name is a little bit confusing, that it is a DDM, direct design method. Probably the name has been given to it because the analysis method is very straightforward and very easy. So the name direct design method has been, I think, obtained from this straightforward method of analysis. Because as you know that in the overall design process, the analysis is one of the major and difficult steps. So if analysis is done easily, then we can say that the overall design process is very direct. So for this reason, this name has been given to it, the DDM or direct design method. Okay, before we start the direct design method, I would like to share some of information about the flat plates and flat slabs, specifically the situations where the flat plates and flat slabs are beneficial to be used. You would have seen high-rise buildings, slabs with beams are given. They are very common. The slab with beams in high-rise buildings are very, very common. However, probably you would have also seen high-rise buildings in which there are no beams. Especially if you search the internet, you will find a good number of buildings where there are no beams. So, where is in which situation we would like to use slab with beams or slab without beams? Which situations? This will depend on many things: economy, the requirements from the client, the financial feasibility, and many other things. The economy, from the economy point of view, the slab with beam system is the most economical system because slab is usually 6 to 7 inch thick and beams are given on the column center line. So weight is also less and the reinforcement requirement and everything is in control. And it is the reason that in most of the high-rise building, slab with beam system is used. Okay. And however, there is one major disadvantage of slab with beam system, and that is that the beam drop below the slab that restricts the headroom, or in other words, it increases the story height from the center of the slab to the center of the slab, from the center of one slab to the center of the other slab above that, which is called as a story height. So this story height is basically controlled by the drop of the beam. So for example, if there is a 20-story building to be designed somewhere, and let's say there are building regulations which restricts the overall height of the building to, let's say, 180 feet or 170 feet. And if the story height is 10 feet, then a 20-story building cannot be constructed in that locality. Because from the architectural point of view and from the functionality point of view, the headroom or the clear space from the slab to the soffit of the beam, the lowest part of the beam, there must be a clear headroom, clear space or clear headroom, at least 9 to 10 feet, somewhere 9, some 9.5 or 10 feet, for the easy movement, functionality, air space, and all these things. So in order to maintain this space, if 9.5 feet is this space below the beam, then if 1 feet is the drop of the beam, so it will be added to this 10.5 6-inch slab. And all this, if all these things are added together, then a story height of around 11 or 11.5 feet will be added, will be needed. Okay, so for 20-story, 11.5 or 11 multiplied by 20 to 20 feet height will be required. And if there is a restriction on the overall height of the building, which, as I said earlier, if it is 200 feet, then only up 16 or 17 stories will be possible to be constructed in that locality. However, if we remove the beams, so by removing the beams, we will get around 1 feet or 8 to 9 inch space. And in 20-story, this will become almost 1 story, or even more than that, 1.5 story. So we can add 1 story or 2 stories if we remove the beams, so which will increase the revenue generation from the project, and it will make the project financially more attractive. So the financial feasibility sometimes depend on the number of stories, because if there are more number of stories, more people can be accommodated and more revenue can be generated. So this is one of the reasons that we would prefer to use slab without beams. This is one reason. And the other reason is also somehow related to this story height, but that will further necessitate the use of the flat plate system. For example, in buildings where there are HVAC, heating, ventilation, air conditioning system, and the building is fully closed, like hospitals, for example. So in hospitals, the heating, ventilation, air conditioning, HVAC systems, they include several pipes around 6 inch to 1 feet diameter. And if you have ever visited an hospital basement, you would have seen these pipes running below the beams, below the slab. So this will further reduce the overall head space. So in that particular condition, these flat slabs will become even more attractive. So in such situations where the building is closed building and the heating, ventilation, and conditioning system is to be provided in the building, then the flat slab without beams becomes more attractive, and slab with beams, they will require even more story height. For this reason, in every important building, especially where the land is very costly, these systems are compared by the designer, and finally the situation is presented before the client, and then it is the decision of the client to which system he agrees. Generally speaking, a slab with beam system is an economical system. Slab without beam will be expensive system because the weight will be more, and the reinforcement to be provided within the slab will also be a little bit more than the slab with beam system. Finally, from the earthquake point of view, the slab with beam system is more efficient than slab without beams system. And for this reason, in most codes around the world, slab without beams system is not recommended to be used in high seismic zones such as zone 3 and 4. corresponding to the Building Code of Pakistan or UBC. However, in Zone 2A and 2B, the flat slab system without beams can be used. So with this background, now we can start our direct design method, which is a method of analysis. Okay, if there are any question, I will give you 5 minutes. You can ask your questions, and then we will continue the lecture. Okay, thank you. If you have a question, you can just tell me your name, and then you can ask your questions. Please. Any question from any student? No questions? I hope you all of you can hear me very clearly.
Yes, sir.
Yes, sir.
Okay. If there are no questions, okay, then we will discuss. We will start discussing the direct design method. Okay.
Okay, sir.
In the lecture before the midterm, where we analyzed and designed slabs with beams using the ACI moment coefficient method, if you remember, panels were analyzed. So the total design procedure was such that panel by panel analysis was done and panel by panel design was made. Okay. In the direct design method, however, frames rather than panels are analyzed. So what is a frame? The total system is divided in frames like this. This is one of the interior frames. Okay. The area located by these red lines, this is one of the interior frame. So these frames are analyzed. An interior frame is analyzed. An exterior frame is analyzed. This is in east-west direction. And another interior frame. This interior frame and this interior frame, they are similar. This exterior frame and these are similar. So one interior and exterior frame along the east-west direction is analyzed. And then we analyze the system along the north-south direction, because this will be a system where you will require designing or providing reinforcement along both the directions. So the analysis will be done along both the directions, interior frames and exterior frames. So when all these frames are analyzed, you will get bending moments, and then the rest of the method is very easy. For every bending moment, you can calculate reinforcement, and you can then provide reinforcement where it is required. Okay, as you know that direct design method is an approximate method now. So you know this, like every approximate method, direct design method has also some limitations, which means that it can be used in certain conditions and it cannot be used in each and every condition. What are those limitations? The limitations are given in this slide. The first limitation is that it can be used only in a situation where live to dead load ratio is less than or equal to 2 and the load is uniformly distributed. The live to dead load ratio less than 2 means that live load shall not be too high. Generally speaking, dead load is much higher than the live load. However, there can be situations like warehouses and storage houses, and especially if there are heavy vehicles to be accommodated in certain floors. So then in that condition, live load can be much higher than the dead load. So if live load is twice of the dead load or more than that, then this method cannot be used. So what method then shall be used? This ACI code recommend that then you should use the exact methods of analysis like finite element analysis, stiffness method, flexibility, and other methods of analysis. So the loads shall be uniformly distributed, loads, no point loads, and live to dead load shall be less than or equal to 2, which is usually the case. So usually in our in practical situations, the loads are uniformly distributed most of the time, and the ratio of live to dead load is also less than or equal to 2. The third condition is that the span shall not vary too much in size. If one span is L1, the adjacent span shall be more than 67% of this, shall not be less than 67% of this, which means that, for example, if this length is 10 feet, let's say, then this length shall be at least 7 feet. If it is less than 7 feet, 6.7 feet, then the difference is more than the 67%, so then the method will not be applicable. Okay, and uh, one of the most strict conditions in the direct design method is the number of panels. The number of panels, slab panels are the spans 1, 2, and 3 shall be at least 3 in both the directions, in X and Y. In both the directions, the slab panel should be at least 3. It is one of the most strict conditions which restrict the use of the direct design method, because in certain conditions, it may happen that along one direction the slab panels are 2, and in the other direction they are 6 or 7 or more. Okay, but in most of the practical situation which we have encountered, the slab panels are 3 or more. So this is also not a problem in practical conditions. So 3 panels in each direction shall be there in order to apply this method. 3 or more spans. Then each panel shall be rectangular or square. They cannot be triangular. A triangular panel will a triangular panel will result due to the placement of columns. Okay, so if columns are placed such that one of the panel is triangular, then the method will not be applicable. And the ratio of long to short side shall be 2 or less. Okay, long to short side ratio shall be 2 or less. So then this method is applicable. This is another condition. Another condition is that all the columns shall be preferably placed on the column's main center line. And the column main center line means where most of the columns are placed. So, for example, if you look at this second row of columns here, where there is an arrow now placed, so 3 columns are placed on this column center line, but one of the column is out of this column center line. The direct design method is applicable if one of the column or 2 of the columns are located outside this main column center line, but then there is a restriction that this offset at which the column is placed or located shall not be more than 10% of the spacing between the columns, adjacent columns. For example, this column into this column, the spacing is, let's say, 10 feet. So this column, if this column is 1 feet or 11 inch, an offset from the main column center line, then the method can be used. Otherwise, the method cannot be used. So these are the limitations of this method, which are covered in ACI 8.10.2 in the ACI 3.18.14 code. Okay, the first step in the direct design method is to select sizes. Basically, this step is not directly related to direct design method. This step is the method. This step is basically the step related to the design of flat slabs and flat plates. If flat slabs and flat plates are to be designed, then the thickness of the flat slab and flat plate shall be initially it shall be assumed using these tables. Okay, if you look at this table, the heading of the table says that it is minimum thickness of non-pre-stressed two-way slabs without interior beam, which means that there are no interior beams. However, exterior beams which are called as H beams, if they are there, then they are this table is still applicable. Then there are two main columns, without drop panels and with drop panels. You know what a drop panel is. Then further, without drop panels, for example, in the without drop panel, there are exterior panels and interior panels. And in exterior panels, further two columns without H-beams and with H-beams. If you remember in my explanation where I was telling you about a comparison between slabs with beams and slab without beams, I said that slabs without beams are preferred in order to reduce the story height. So if beams are provided at the perimeter of the building, which are called as H-beams, and so they will not restrict the overall height of the building because they are at the exterior edge, and at the exterior edge the walls will be provided, so they will not restrict the overall height. However, if they are provided somewhere interior, inside of the building, then they will restrict the overall height. So there are a lot of advantages if H-beams or perimeter beams are provided at the periphery of the building. So if the H-beams are provided, then these are the equations to be used. If H-beams have not been provided, these are the equations to be used for interior panels. These are to be used with drop panels. These are to be used without H-beams, with H-beams. Okay. Okay. Now, most of the time, what we do is that we select the size which gives us maximum thickness in our routine designs. Okay. Academically, however, you should use the relevant column carefully, and then finally you can decide yourself. Usually, we prefer to use more thickness in our design projects, okay, because it has advantages, many advantages. So you can use the relevant equation. Ln by 33 means what? Ln by 33 means that is, if the slab panel is let's say 33 feet long, which means the distance between the two columns, then 33 by 33 feet is 1 foot. So 1 foot thick slab will be required. You can see that in the previous slab, in the previous examples where slab was having beams also. So in a slab with beam system, most of the time the slab was 6 to 7 inch thick. However, here when there are no beams, then the slab is 12 inch thick. So it becomes 12 inch thick when it is 33 feet long, and so on. The minimum thickness is per ACI code for slabs without drop panel shall be 5 inches, and with drop panel shall be 4 inches. So with these relevant equation, you can initially select the size of the slab. The load can be calculated from this equation, 1.2 DL plus 1.6 live load. Dead load can be calculated from the superimposed dead load, and the self weight of the structure. Live load can be taken from the AC. Then ultimate load can be calculated using this equation. Okay. Then in the third step, analysis step, so it is the third step where we will be actually using the DDM direct design method, which I said now quite a few times. It is a method of analysis. Okay. So as I said earlier, that interior, the system will be divided into frames, interior and exterior frame, both along east, west, and north-south directions. So first of all, we will divide the slab system into frames, interior as well as exterior. How? Like this. First of all, for an interior, for marking of an interior frame, along the east-west direction, we will mark a column center line as shown in this animation by the yellow dashed line. Then we will draw another line on one side of the column center line in half of the panel, which is called as panel center line, as shown by the red solid line. Then another line will also be drawn on the other side of the column center line at the panel central line. So this will become now an interior frame. So the marking of an interior frame is being completed, which is the first step, interior frame. Okay, the width of the frame is called as L2. Width of the frame is called as L2, and the length of each span is also called as, and the length of each span is called as L1, L1 and L2. Okay. Okay, and if panels are different in sizes, adjacent panel, for example, if this panel is 20 feet and this panel is, let's say, 24 feet. So this L2, in this, first of all, let's see in this case. In this case, this panel is also 20 feet and this is also 20 feet. So 20 divided by 10 and 20 divided by 10, the panel width is, the frame width is L2. However, if the panels are not of the same size, then the average of these two will be taken as L2. 20 feet, let's say, and 24 feet. So average of 20 and 24, 20 plus 24 divided by 2. Okay, this will give us L2 on the width of the frame. Okay. Marking of an east-west exterior frame, the column central line is drawn. Then the panel central line is drawn on one side of the column central line. Which is drawn at half width of the panel. Then on the other side, there is no panel. The frame will be completed by drawing another line at the exterior edge of the columns. So from the column center line to the exterior edge of the column, there is only half the column width. This half column width will be added to this half width of the panel, and this will become L2 for the exterior frame. Panel width divided by 2. This half panel width divided by 2 on one side, plus half of the column, because from the yellow line, which is the column center line, this panel extends up to half of the column size. If there is any slab extending beyond the edge of the column, then it will be treated as a cantilever slab, and it will be analyzed and designed separately. It will not be part of the flat slab's exterior frame. Okay, now in the next step, when the interior frames and exterior frames are marked, then within the interior frame or exterior frame, there is further marking of the strips, which are called as column strips and middle strips. Okay, the column strip is the strip which has been shown in this slide by the green color. Half the column strip extends on one side of the column central line, and half of the column strip extends on the other side of the column central line. This patch of the, or strip of the strip bound between the yellow lines and the green color is the column strip. The total column strip consists of two column strips, half column strip on one side of the column central line and half column strip on the other side of the column central line. And half of the column central line, is equal to least of L1 by 4 or L2 by 4. L1 is this length, and L2 is the width of this frame. In this particular case, as shown in this slide, the L1 is 25 feet and L2 is 20 feet. So least will be the least dimension. L2 is 20 feet. So it will be 20 divided by 4. So half the column strip will be 5 feet. And on the other side of the column center line, half the column strip will also be 20 by 4. It will be 5 feet. The total column strip will be 10 feet. Okay, and the remaining portion of the frame on both sides will be half middle strip on one side here and half middle strip on this side. As shown now. Middle strip divided by 2, half middle strip and half middle strip here. So the total frame width is divided into two strips: an interior column strip, which is a strip close to the column, and a middle strip which is away from the column. Okay, it is away from the column, but it is basically the mid portion of the panel. It is the mid portion of the panel. This is total panel. This is total panel, and this is mid portion of the panel. So that is why it is called as middle strip. This subdivision of the frame into column strip and middle strip is necessary because the column strip contains columns, and this is stiffer in the middle strip. Therefore, most of the bending moments will be attracted by the column strips. So it is necessary to divide total frame into column and middle strips. Okay. So once this is completed, then we will move ahead. This is an example. As I said earlier, the column strip 20 by 4. So 5 feet on this side, 5 feet on this side. Okay, 10 feet, half. Then middle strip, half middle strip. The total width of the frame is 20 feet. 20 minus 10, which is column strip. So this will be 20 minus 10 is 10. 10 divided by 2, half middle strip on one side and half middle strip on the other side. So 5 feet, 5 feet are 2 middle strips, and the interior column strip is 10 feet. Okay, for this particular situation. The exterior frame, column strip will be equal to panel width divided by 4, because column strip will extend only on one side of the column center line, and on the other side it will be the panel. There is no panel on the other side of the column center line. There is only an extension of the slab to the column edge. This will be added to this column strip. So the portion of the slab on one side of the column center line, half of that will be added to the column strip, and the remaining portion from on the other side of the column strip up to the column edge will also be added to this to make a column strip of the exterior frame. So a column strip in this case is minimum panel width divided by 4. Panel width is 20. 20 divided by 4 is 5 feet. So 5 feet plus half of the column. From the column center line to the exterior portion of the exterior edge of the column is half the column. This will be column strip. And the middle strip will be L2, width of the exterior frame minus the column strip, like this. So this has been demonstrated here. That L2, which is the width of the exterior frame, L2 is basically this total width. So on one side of the column center line, half the width of the panel. Half the width of the panel is 10 feet. 20 divided by 2 is 10. Plus the portion of the slab extending outside on the outside of the column center line to the edge of the column. So to the edge of the column, this is only half column. So half the column will be added to this half. So the total width of the exterior edge is 10.5 feet, and the column strip out of this is 20 divided by 4 plus half the column. 20 divided by 4 is 5 plus 0.58, 5.58. And middle strip is 10.58 minus 0.58 is 5 feet. So this remaining portion is middle strip, which is only on one side in the exterior frame case. It is 5 feet and it's 5.58 feet. Okay, next is now once the frames are marked, we will start the analysis. And within the analysis, this is basically step number 3, where a static moment m0 is calculated. Static moment m0, which represents the moment in this whole panel. Straight from one column to another column. This m0 moment is given as WU L2 LL square divided by 8. WU L2 LL square divided by 8. L2 is width of this panel frame, and Ln is the clear length. Okay, and WU is load per square foot. This will give us total. This is called a statical moment. Total statical moment in this span. Once we obtain this moment from this equation, then the total moment, static moment WL square by 8 will be distributed longitudinally to negative and positive bending moments. You know that at the supports we have negative moments and at the midspan we have positive moments. So on both the supports, on both side of this span, the negative bending moments M negative and M negative will be equal to 0.65 m naught and M positive will be equal to 0.35 m naught. And you know M naught is static moment, WU L2 ln square by 8. So this is called as longitudinal distribution. Further, this longitudinal distribution will be further these longitudinal moments will be distributed laterally. This is called lateral distribution to the column strip and middle strip. And the total bending moment, which was 0.65 m naught here, total bending moment 0.65 m naught here in this portion. Of this 0.65 m naught, 75% of this 0.65 m naught will be given to the column strip negative moment here. Okay, and the remaining 25% will be divided equally on both sides of this column strip to the middle strips. 12.5% on this side and 12.5% on this side. Similarly, positive bending moment will be basically 60%. 60% of what? 60% of this total 0.35 m naught. 60% of 0.35 m naught will be given to the column strip, and the remaining 40% will be equally divided among the two middle strips. Okay. Similarly, on the other side, the negative bending moment will be distributed in the same manner. The total bending moment 0.65 m naught will be 75% of that moment will be given to the column strip, and the remaining 25% will be equally divided among the two strips. What does it mean actually? If there is a moment of 100 foot kick, let's say total WUL m naught, if m naught is 100, if m naught is calculated as 100 foot kick, then out of this 100, 65 will become here, 65, 35 will come here, 65 will come here. Total 65, 35, and 65. And then out of this 65, then out of the 65, 75% will be given to the column strip. So 0.75 into 0.65, this will go to the column strip. Okay, 0.75 into 0.65. 0.75 into 0.65 is 0.4875. So 0.4875, 0.4875. Okay, will become here, which means around 48.75 foot kick bending moment will come here. The remaining is 100 minus 0.25 into 0.65 is 0.1625. 0.1625 divided by 2, which means 0.08125. So 8 foot kip will come here, 8 foot kip will come here, and 48 will come here in this degree. So when we want to design this frame, so this column strip will be designed for this 48 foot kip bending moment, and the middle strip will be designed only for 8 foot kip. So which means that a lot of reinforcement will be required here, a stop bars in the column strip. Okay, this you will see in the coming slides. This was for the interior span. For an exterior frame, the total static moment will remain the same, WUL2 ln square by 8. However, the longitudinal distribution is different. Exterior is 0.26 m naught instead of 0.75, and then positive is 0.52 instead of 0.35, and the other negative is 0.7 m naught. Okay. Further, this will be distributed to column strip and middle strip. The exterior negative will be 100% taken by the column strip, 1 m negative. So this is 1. 0.26 will completely be taken by the column strip with 0 in middle strip and 0 in middle strip is negative. And in the positive 0.6 m exterior, 60% of this 0.52 m naught will be given to the column strip here, and the remaining 20 will be given. 20% of this 0.52 will be given to the middle strip. Similarly, 0.75 m naught, 75% of this 0.7 m naught will be given to the column strip, and the remaining 12.5 will be given to them. Okay, finally, this is now slide number 27, where all the coefficients are given. You should write down all these coefficients in your notes, okay, in 5 minutes, and then we will. So there will be a 5-minute break now. In this break, you should write down these coefficients in your notes, because we will be frequently using these coefficients. And in the direct design method, this is the only new step for you. The rest of the method is very easy. Once the bending moments are calculated using these coefficients, the rest of the method is the same. By the same, I mean that when bending moments are calculated, the reinforcement will be calculated by height and trial, which you know very well. Okay, so you should write down these coefficients in your notes for reference. Okay, and these basically the slide number 27 is more or less a summary of the direct design method, where all the coefficients are given. M naught, you know, is W U tilde square by 8. M exterior here is total 0.26 M naught. Then we have 0.52 M naught here. Then we have 0.7 M naught here, 0.65, 0.35, 0.65. These are the longitudinal distribution coefficients. And the later distribution coefficients are 1 of this and 0.6 of 0.52. The remaining will go to the middle strip equally. 0.75 of this, 0.7. 0.75 of 0.65. 0.6 of 0.35, okay, so on. So you should write down these coefficients in your notes, and then you will resume the lecture after 5 minutes.
तो सर बाहर चले गए, अगर कोई क्वेश्चन हो तो मुझसे पूछे।
सर जब ये कॉलम सेंटर पे वो फोर्स ले लेना
जी
सर, ये जब सारे मूवमेंट्स आ जाएंगे ना सर,
जी जी
तो फिर अगर लेट सपोज ये वाले तो ये फर्स्ट वन तो वन मतलब 100% ले रहा है ना
बिल्कुल, वो कॉलम स्ट्रिप 100% ले रहा है सर।
सर। अगर ये दूसरा वाला कॉलम स्ट्रिप जो है ये 60% ले रखा है, तो ये बाकी जो है 40% हम टू पे डिवाइड करेंगे, ऊपर और नीचे वाला।
और मिडिल स्ट्रिप की बात कर रहे हैं, मिडिल स्ट्रिप के लिए 2 पे डिवाइड करें ना, जो बाकी रह जाए, ये 60% ऑफ एम एक्सटीरियर है ना, इससे ये एम नॉट से 52% फाइंड करें इससे, सही है। तो ये आपके पास ये एम एक्सटीरियर पॉजिटिव आएगा,
ओके ओके सर।
सही है। एम नॉट आपने
ओके
आपने फाइंड किया, फिर ये 0.52 के साथ मल्टीप्लाई करें तो आपको ये वैल्यू देगा, एम एक्सटीरियर पॉजिटिव, ये पॉजिटिव वैल्यू देगा। लेकिन वो इन सब के लिए ये एरिया है ना, ये रीजन, इन सब के लिए ये वैल्यू होगा। फिर इसको 60% ले लें, और वो 60% इस कॉलम स्ट्रिप में चला जाएगा, और बाकी जो 40% है वो 2 पे डिवाइड करें, 20% इधर आएगा और 20% इस रीजन में आएगा, मिडल मिडल स्ट्रिप के लिए।
ओके सर, समझ गया सर।
कोई क्वेश्चन है जी? ये क्लियर है?
Okay, so let's move ahead now with the remaining part of the lecture. Here's an example with the given statement that we are required to analyze the flat plate shown below using DDM. The slab supports a live load of 144 pound per square foot. All columns are 14 inch square. FC prime is 4 kSI and FY 60 kSI. Unlike many other examples, here the live load is 144 pound per square foot. And this is because the example statement is being taken from the Nelson book, where the load is 144 pound per square foot. Otherwise, in most of the cases, the live load will be less than 100 pound per square foot, or even less than 70 pound per square foot in most of the buildings, except where there is a warehouse or heavy machinery is to be kept in the building. Okay, so first of all, we will now select the size of the slab using this table. Since there are no drop panels, it is a flat plate system. So in a flat plate system, the relevant equations without drop panels and for exterior panel. Exterior, if you look at the exterior panel equation, they will give us more thickness than that of the interior panel. And because in most of the conditions, in almost all the conditions, we will keep a uniform thickness of the slab. So for that reason, the exterior panel thickness will govern. The exterior panel, from the exterior panel without edge beams and corresponding to grade 60 steel, the relevant equation is ln by 30, and for interior panel it is ln by 33. ln by 30 will give us more thickness, so we will use this equation in our calculations. ln by 30. ln is clear length. Clear length is calculated from the center to center length of 25 feet. 25 feet minus the one column size, which means half the column on one side and half the other on the other. Half the column means 14 divided by 2 and further multiply by 2. This 2 will be cancelled with this 2, so one column size will be subtracted from 25 feet, and then this will give you the clear length. This clear length will be divided by 30, then multiplied by 12 to give us thickness in inches. The minimum thickness required is 9.53 inch. We will round this up to 10 inch and use 10 inch thick slab. For effective depth D, you would have seen in the slabs, two-way slabs with beams, that we use average D, and average D in this case is calculated in this manner, that from the overall thickness of 10 inch, 0.75 inch clear cover is subtracted, and then one diameter of the bar, complete one diameter of the bar is subtracted. So this D is then average D. 10 minus 0.75 minus 0.75 is 8.5 inch. Effective depth, average effective depth is 8.5 inch, which will be used for designing or reinforcement calculation along both the directions. In the calculation of load, service dead load is the slab is 10 inch thick. 10 divided by 12 into the density 0.15 kip per cubic foot will give us 0.125 kip per square foot load, or 125 pound per square foot. Superimposed dead load is not given in the question, although in every design example there will be some superimposed dead load. But anyway, this is a demonstration. So in the demonstration, sometimes the superimposed dead load may not be used. However, in practical cases, in almost every case, superimposed dead load will be there. Okay, a service live load. A service live load of 144 pound per square foot is given in the example. With these two, the service dead load and service live load, we will calculate the ultimate load, 1.2 times 0.125 and 1.6 times 0.144. This gives us a 0.3804 kip per square foot, which means 380.4 pound per square foot on every square foot of the slab. The load is 380 pound, for which it is to be designed. Next is the steps for analysis, marking of the interior frame, which we have discussed in the previous slides. Interior frame, okay, in this manner. Marking of the column strip. Okay, this we have seen in the previous slide, 10 feet column strip, because the dimension of the slab are the same as those as mentioned in the previous slides. So column strip is 10 feet and middle strip is also 5 feet, 5 feet. Next is the calculation of M naught. M naught is WU L2 Ln square divided by 8. WU is 0.3804 kip per square foot. L2 is 20 feet. And Ln is 25 minus 14 divided by 12. Is 23.83. 23.83 square divided by 8. So total M naught in the exterior span as well as the interior span of the frame is 540 foot kip. Then we will further distribute this M naught in both the spans longitudinally as well as laterally. The longitudinal distribution is done in this manner. 0.26 M naught, this 0.26 of 540. 0.26 of 540 is 140. 0.26 of 540, 0.52 of 540 is 281. 0.7 of 540 is 378. So this total is 140. This is total, this yellow exterior, this total is 140, this thing, okay. 281 will come here in this region, 378 will come here, 351 will come here, 189 will come here, and then 351 will also come here. These are the longitudinal distribution. In the next step, lateral distribution will be done. This is longitudinal distribution. Lateral distribution will be done according to the coefficients for the column strip only. The middle strip bending moment will be obtained from the total bending moment in that portion minus the column strip. So this is 1 M exterior negative. So which means this 140 completely will come here, 140. And this 281.52 M naught will be multiplied by 0.6. 0.6 times 281 will come here. The remaining will come to the middle strip. Similarly, 0.75 multiplied by 378 will come here. The remaining 12.5 multiplied by 378 and 12.5 multiplied by 378 will come to the middle strip. So on. So this will be like this. 140, this is 169. 169 coming from this value. And next is 284, 263. All the values of the column strips are shown now in this slide, column strip only. The middle strips values will be obtained from this 140 minus 140, so 0 and 0. 281 minus 168, and then divide by 2, half here and half here. 378 minus 284, and then divide by 2, half here and half here. 351 minus 263, half here and half here, so on. So the final value will be like this for the column and middle strips. Okay. Further, these bending moments, 140 bending moments is a bending moment in this whole strip, negative bending moment in the whole strip. Okay, where the strip width is 10 feet. So further, this 140 will be divided by 10 in order to obtain per unit width bending moments, per unit width. And similarly, 168 will be divided by 10. This 12 divided by 2 will be divided by 5, because the middle strip is 5 feet wide in this region. This is 5 feet wide. So further division by the relevant strip width will give us per foot width bending moments in this form, 14, 16, and so on. Okay, so this will complete the analysis along the east-west direction of the interior frame. Now, east-west direction in the exterior frame. Interior frame was completed, now exterior frame. The exterior frame L2 is calculated in this manner. L2 is half panel width, 20 divided by 2, so it is 10, and half the portion from the column central light to the exterior edge, which is half the column. This is half 14 divided by 2, 10.58. Column strip is calculated. The column strip, as we said earlier, that it will be minimum panel width divided by 4. Panel width is 20 is minimum. 20 minimum panel width means 20 and 25 are two sizes of the are length of two sides of the panel, and the minimum of these two is 20. So 20 divided by 4 is 5, and plus half the column size. So this is 5.58. 5.58 column strip. And the middle strip is 10.5 minus this, it is 5 feet. Then M naught will be calculated WU L2 ln square divided by 8. WU L2 ln square divided by 8. WU is 0.3804. 0.3804. L2 is 10.58. 10.58, and ln is the same, 23.83. 23.83 square divided by 8. So this total bending moment, static moment, M naught is calculated this time, but with different L2. Now this is almost half of the previous M naught, which was 540, almost half of that. Okay, and then it will be literally in longitudinally and laterally distributed. Longitudinal distribution is with these coefficients 0.26, 0.52, and 0.7, and this, and then we have lateral distribution of this. Lateral distribution is such that exterior column strip is completely taken, this whole bending moment, 74, 100% of this, then 0.6 of 148, 0.75 of 200, 0.75 of 186, 0.6 of this 100. And the remaining will be given to the middle strip. So 74 minus 74 is 0, 148 minus 89 is 59, 200 minus 150 is 50, 186 minus 140 is 46, and 100 minus 60 is 40. These middle strips bending moments are calculated. Then further, the moments are calculated per unit strip width. You know the column strip and middle strip width, divide the bending moments by the relevant strip width, and the bending moments per unit width will be obtained. Next is the calculation of bending moments along the north-south direction interior exterior frame. I will advise you that you practice this north-south interior frame as well as exterior frame, and after you finish your calculation in 10-15 minutes, I will share the results with you so you can compare your values. Okay, you can compare your values with us. It will build your confidence and will further increase your understanding and the method. So please practice this on the north-south interior frame in 10-15 minutes for the interior frame as well as for the exterior frame, and then we will share the values with you. Okay, so don't waste your time. You practice this, and the method is very easy, very straightforward of the analysis. After you complete this, then we will present the values of both the directions in one slide, and then we will try to start designing the system. Okay, so please do this.
इस प्रॉब्लम के हवाले से अगर कोई क्वेश्चन हो तो फिर मुझसे पूछिए, मैं इधर हूँ, मौजूद हूँ। अगर इस प्रॉब्लम में अगर आपने सॉल्व किया और इसमें कोई इशू हो आपको, फिर मुझसे पूछिए।
Okay. So let's move ahead with the remaining part of this analysis. M naught is 421.5 foot kip for interior frame. These are the values. Now you can compare your calculated values with these values. These are per strip width values. Now for the exterior frame, these are the values. Okay, finally, we can write down all these values for north, south, in east-west direction on one sheet like this. All these values are corresponding to the east-west direction. Okay, so now you should pay attention to these values. Okay, how finally we assemble all these values. These are the values that we have obtained for column strip in one of the interior frames along the east-west direction. 14 foot kip, 16.8 mid spin positive bending moment, 28.3 and 26. Out of these two bending moments, we will take 28.3. We have 11.3 positive bending moment here and 26.3 bending moment. Okay. Coming to the middle strip for the interior frame, we have 11.2 foot kip here, 0, 0. First of all, 0, 0 negative, and then 11.2. 11.2 is also here. Okay, on the other side of this column strip within the interior frame. But for the purpose of clarity, we have not written these values. Similarly, 9.4 is also here, 9.4, and 8.8 is also here. Out of these two values now, this 11.87 is coming from the exterior frame analysis, and 11.2 is coming from the interior frame analysis. But both the values are corresponding to the mid-span positive bending moment in this panel, which I'm going to hedge now, in this panel. This panel, exterior panel. In this panel, this 11.87 and 11.2 are two values corresponding to the mid-span positive bending moment. We will select only one value. So we will obviously select 11.87, and this we will design this for positive bending moment in the mid-span. Similarly, out of these 10, 9.4 and 8.8 and 9.2, we will select 10, and we will select this. We will design this negative bending moment in the middle strip corresponding to the bending moment of 10 foot kip, and so on. If you look at the bending moment in the exterior column strip, in the exterior frame column strip, so the value 13.86 is very close to 14. 15.94 is very close to 16.8. 26.8 is very close to 28.3, which means that regardless of the width of the frame, the per unit width values of the bending moment in the column strip of interior frame and exterior frame are almost same. So, okay, these now we will start designing the slab along the east-west direction and north-south direction separately. First of all, we will design along the east-west, and then we will design along the north-south direction. Okay. If you want to draw the bending moment diagram for this column strip, you know 14, 16.8, 28. So we can draw the values like this in the column strip. Interior column strip, and then we have interior middle strip. Okay, 14, 16.8, 28.3, 26.3, 11.3, and so on. These are the interior column strip bending moment diagram. And for the interior middle strip bending moment diagram, we have 0, 11.2, and so on. These are the sheets. So once we have the bending moment diagram for the column strip and middle strip separately, you can design these column strip and middle strip using the hit and trial procedure that you already know. By using the hit and trial procedure for, first of all, let's say for 14 foot kip, you multiply this by 12, you will get the inch cap bending moment. Assume small a and find out A's and so on. For the north-south direction, the same procedure will be used. Okay. And the bending moment diagram for the interior column strip and the intermediate strips are also given. Next is the design. The design final outcome has been given on this slide. However, to reach this outcome, you will have to first of all select the bending moments for design, and I will share with you these one of the I will demonstrate the reinforcement calculation for one of the bending moments, and the rest you can do yourself. So I will just do this column strip, interior frame column strip, and I will go back to the bending moments of the column strip are here. These are the bending moments 14, 16.8. So now you first of all look at the bending moments 14, 16, 28. This 28 is almost double of 14. 16.8 is positive bending moment, 11.3, 11.3. Okay, so let's start with the bending moments of 28.3. First of all, we will calculate reinforcement for 28.3 because it is the largest bending moment in the column strip. This is the largest bending moment. So the advantage of designing for this largest bending moment will be that we will come to know which reinforcing bar will be appropriate to be used. Because if we try using number 4 bar, let's say for 14 foot cap or for 16.8 foot cap, and the spacing is very close, then we will decide in the spacing for if we use number 4 bar for 14 foot cap, and then while designing 28.3, if the same bar is used and the spacing become very close, we have to redesign the whole, or we have to revise the whole design, because it will not be possible, especially for positive bending moment, to use different diameter of the bars in different spans. For negative, you can use sometimes, but for positive, it will be difficult. And it will be always good to use one bar, which I mean by one bar, I mean one diameter of the bar in the whole, in all the spans. Okay, because this will otherwise, economize the project. By using different diameter of the bars, there will be difficulty in placement of the bars, purchasing of the bars. This will be difficult. So instead of using different diameter of the bar, in this particular case, we will try to use one diameter of the bar. So let's demonstrate one design to you. 28.3 is M view, 28.3 foot cap. We will convert this into inch cap by multiplying this with 12. Okay. 28.3 into 12 is 622.6 inch cap. Okay. We will assume now let's A is 1 inch. You can calculate A is 622.6 divided by 0.9 divided by 60 into D. D, you know, is 8.5 minus 1 divided by 2. So 0.9 into 60, and then we have This comes out to be 1.44 square inch. 1.44. We'll calculate small a, ASFY. Huh?
28.3 multiplied by
339, okay. 28.3 into 12. 339, okay, I'm sorry, 339. 339, let's say it's 340. So this will become 340. 340 divided by 0.9 divided by 60 and then divide by 8. 0.787. 0.787 into 40. That's number SFY divided by 0.85. SC prime 4. $1.157. 1.157 inch. Although the difference is not too much, but we will do another trial to see what happens with another trial. So the other trial, we will use small a equal to 1.157. Is for second trial comes out with 0.79. And small a will again then will come very close to this. So let's say AS is equal to 0.79 square inches collected. Then we will select this, we will decide the spacing based on the diameter of the bar. Let's say we want to use number 6 bar, number 5 bar. Let's say number 5 bar. You know that number 5 bar has an area of 0.3 square inch. The area of bar, spacing is area of bar divided by area of steel, 0.3 divided by 0.79 into 12. It comes out to be around 4.5 inch, 4.5 inch, 4.5 inch center to center. So it is the closest spacing that you can come across in this whole design, because 28.3 is the largest bending moment. All the spacings will be less than this. Okay, for the rest of the bending moments, what you can do is that you can use the unit rule. 28.83 foot kip for 28.83. What is the unit rule? I will show it to you right now. Unit rule is like this. For 28.3 foot kip, 28.3 foot kip, area of steel is 0.79 square inch. For 16 foot kip, it will be equal to how much? 16 into 0.79 divided by 28.3. Into 0.79 divided by 28.3. 0.446 square inch. Okay, and similarly, for all other bending moments, you can use this unit rule, find out the area of steel using number 5 bar, find out the spacing. You can complete this design along both the directions, and finally you can compare your outcome of your design with our design, which we have presented in this figure. For the column strip, number B means number 5 at the rate of 8 inch center to center. So we have number 5 at the rate of 8 inch here is top bars, is top bars. Okay, this is bottom bar, and A is also top bar. C is bottom bar. So A is number. You have seen that for this bend moment, the spacing was coming out to be number 5 at the rate of 4.5 inch centimeter, but we have chosen number 5 at the rate of 4 inch centimeter. Okay, slightly on the higher side. And for B, because this bend moment was almost half of this, so the spacing will be double. So number 5 at the rate of 8 inch centimeter is being used here. For the rest, you can check yourself, and you can come up with your questions. Next time we will leave this lecture at this point. Okay, and then we will try to complete this in the next week. Okay, so you should try this, try to understand this method. Okay, and try to design this slab. The slide 59 and 60 gives a summary of the design. You can what you can do is you can try another diameter of the bar. Number 5, instead of number 5, you can use number 6 bar, number 4 bar, number 7, and number 8 bars, and you can come up with different spacing. It is allowed as long as the spacing is not more than the maximum allowed. Okay, you should complete this. Now we will leave the lecture at this slide, and we will complete this in the next week, inshallah. Assalamu alaikum and Khuda Hafiz. Thank you.